right, so you have 11.2 gravitational field. We've been talking about gravity for a while. I want to revisit a few ideas. Oh, by the way, I've got some missing labs. They're on the board. If you're on that list, I need those in, please, ASAP. Let's talk about gravitational field, and then we're going to talk some more about weight and weightlessness. And that's basically it for gravity. Then we'll get into friction, and then we'll have our test. So, okay, so the Earth pulls on the moon. We already know that. That's what keeps the moon in orbit, right? We regard this as action at a distance. Action at a distance, because the Earth and moon interact with each other even though they are not in contact. This idea of action at a distance is sort of a big idea. It's the whole idea of fields, the field concept. There's gravitational fields, there's electric fields, which is next. There's magnetic fields, which we hope to get to. Okay? It's, like I said, action at a distance, being able to apply force without touching it, using the force. Or we can look at this in a different way. We can regard the moon as interacting with the gravitational field of the Earth. So, in other words, or a rocket, right, whether it's a rocket or whatever, there is this gravitational field around the Earth that is represented by these lines, which I've drawn incorrectly, by the way. Okay? So the field spreads out, and as we get farther away from the Earth, what does it do? It gets weaker, inverse square law. We've had this discussion already. The properties of the space surrounding any mass can be considered to be altered in such a way that another mass introduced to this region will experience force. When I bring in this rocket ship, it will experience a force, right? As this guy gets closer, he experiences more and more force. Way over here, much less force. Is the gravitational field still existent out there? It is. It's just that the field lines are, remember, far apart, right? The farther apart they are, the weaker the field is. It's common to think of this in rockets and space probes interacting with gravitational fields rather than with the masses of the Earth and other planets or stars that are the source of these fields. The field concept plays an in-between role in our thinking about the forces between different masses. So it allows us to sort of explain how this force can be exerted without any touching, because we would say that the rocket ship or the moon or what have you is touching the force field. So it's an imaginary thing, it's a model, it's a way of describing it. Is this useful at all? Have you seen Apollo 13 with Tom Hanks and Kevin Bacon and that other guy? Yeah. Okay. So when they sent it to the moon, they couldn't land on the moon, they had to bring them back. And the only way to get enough sort of acceleration of force to turn around was they actually had to go all the way around the moon. They interacted with the moon's gravitational field, and what did it do? It pulled them and turned them around. They were halfway there, and they knew they weren't going to land, but they had to go all the way there so they could turn around. Just like, you're driving along, you have to turn around, you got to find a safe place to pull a U-turn. Same idea. Okay, so they interacted with the moon's gravitational field. When they send out a probe, like that one that just landed on Mercury a couple days ago, or a couple weeks ago, they would send it out. Do they send it right at Mercury? No, just like Billy going for a pass, right? The quarterback Mitch has to throw not where Billy is, they have to throw where he's going to be. Same idea, right? And they would actually use the gravitational fields to pick up speed. Okay, I'm off on a rant there. A gravitational field is an example of a force field for something in the space experiences a force due to the field. Another force field you might be familiar with is the magnetic field, and we're going to look at those in the future. I'm going to skip over this a little bit here, okay? We're going to see pictures like this. You're going to see magnetic field pictures like that. Do these fields exist around masses? Not magnetic ones, but gravitational ones, yes. The patterns of the Earth's gravitational field can be represented by field lines, figure 11.4 right here. Like the iron filings around a magnet, the field lines are closer together where the gravitational field is stronger. Hopefully you know that already. Is that something that might be tested? The field lines are closer together where the gravitational field is stronger. Yes, that is something I expect you to know. At each point on a field line, the direction of the field at that point is along the line. Arrows show the field direction. And everything gravitationally is always going to be attracted, right? If you've got electric charges, which we're going to be looking at in the future, there could be pushing away or attracting, magnetic, pushing away or attracting. Gravity only attracts. A particle, astronaut, spaceship, or any mass in the vicinity of the Earth will be accelerated in the direction of the field line at that location. The strength of the Earth's gravitational field, like the strength of its force on objects, follows the inverse square law. What do I mean by that? Inverse square law means 2 times as far. If you double the distance, 1/4 the strength. Where did I get 1/4 from? Inverse 1 over squared. 1 over 2 squared. 3 times as far, 1 over 3 squared, 1/9. 4 times as far, 1 over 4 squared, 1/16. The moon is a long ways away. Is it 9.8 way out there? No, but it's enough to pull it in. Do you have this picture? Oops. Do you have this picture on yours? This one down here? No? Maybe on the next page? Okay. Here it says the space shuttle is caught in the field of Earth. The moon is caught in the field of Earth. I'm feeling E's gravity. It's getting stronger as I fall toward E. So it's just another description of that, right? Notice all the arrows point towards Earth. Where is it strong? Here, where they're close together. Where is it weak? Here, where they're far apart. Morning, Mike. Okay, now you've all wondered, probably as a kid, what would happen if I dug a hole all the way through the Earth, right? Every kid has wondered that. I'm going to tell you. Okay. Is there? Maybe we can find it later. Okay. Here's the part where you gotta listen. So yeah, you probably have a little cell phone break there. Kind of put it down. Refocus. The gravitational field of the Earth exists inside the Earth as well as outside. It doesn't end, right? Like if you dig a hole, even if you go in your backyard and you dig a little tiny hole, there's still gravity there, right? To investigate the field beneath the surface, imagine a hole drilled completely through the Earth, and we're going to say from the North Pole to the South Pole, just for simplicity's sake. Forget about impracticalities such as lava, high temperatures, lack of bathroom facilities, what have you. Consider the kind of motion you would undergo if you fell into such a hole. If you started at the North Pole end, you'd fall and you would gain speed. Why? You're being accelerated by gravity, right? You would fall and gain speed all the way down to the center, overshoot because you're going really fast, and then lose speed. You would slow down as you went all the way up to the South Pole. So you would speed up, speed up, speed up, speed up, speed up, slow down, slow down, slow down, slow down. No different than if you were to take a tennis ball and throw it up, right? Same idea. Where is the acceleration zero? You can't see it on the screen very well, but on your page maybe you can. Where is the acceleration zero? Right in the center. Now, does that mean you'd hover there and just sort of float around in the middle of the earth?
No,
you just stop accelerating. It's not how fast you're going, it's how fast you're changing speed. Okay? So, you'd gain speed. If you start at the North Pole, you'd fall, gain speed all the way down to the center, overshoot, lose speed all the way up to the South Pole. You'd gain speed moving toward the center and lose speed moving away from the center. Without air drag, the one-way trip would take nearly 45 minutes. You would fall, free fall for 45 minutes to the other side. Okay? Yes, free fall. If you failed to grab the edge, you'd fall back towards the center, overshoot, and return to the North Pole at the same time. That is assuming that the Earth is perfectly round. It's not, right? Okay. If you do assume the Earth is completely round, and you were to jump in the hole, 45 minutes later, Graham's walking down the street in Australia, right? And what would you see when the person popped up the hole? What would you see? It's a dead body. It's only 45 minutes. Would they come out and give you the wave like this? No. Feet first. You'd be walking along and all of a sudden, whoop, up would come this person, feet first, upside down. And then he would fall back down again, right? You failed to grab the edge.
You'd be trapped.
Would you be trapped in this hole? You'd have to do what? You'd have to grab the edge or somehow grab a hold of something when you come flying out, right? Otherwise, you're just going to go right back down again. And all the way back up. And then when you pop out here in Dauphin, would you be right side up?
Yeah.
So you're ready. As long as you went like this the whole way, right? didn't tumble, I suppose.
And no air.
Okay. Now, if you repeat this trick with an accelerometer of some kind, your acceleration at the beginning of the fall is g, but you'd find it progressively less as you continue toward the center of the Earth. Stop and think about this. Mr. Bennett, you said the farther away we get, the less it is. The closer we get, the more it is. How come if you get closer to the center, it's less? It's pulled both ways. You have mass both above you, above in air quotes, and below you, exactly. Right? Because you're being pulled downward towards the center, you're also being pulled upward by the part of the Earth that is above you. In fact, when you get to the center of the Earth, the pull down is balanced by the pull up, and you're pulled in every direction, and the net force on you is zero. There is no acceleration as you whiz with maximum speed past the center of the Earth. The gravitational field of the Earth at its center is zero, oddly enough. Okay? So, yeah, there'd be some magical place somewhere right there where gravity would be about half 9.8, about 4.9. The strength of the gravitational field at any point is measured by the force on a unit mass there. If a force F is exerted on a mass m, the field strength is F over m, and its units are newtons per kilogram. So that whole 9.8 meters per second squared is for acceleration, but it's also for bathroom scales, right? The gravitational force on me is 9.8 newtons per kilogram. 810 newtons. Going the wrong way. What if you were able to climb a ladder all the way down to the center of the Earth and then jump off? You're exactly in the center. What would happen? You would truly float and be waves, right? Yeah. You'd be covalently bonded, is that what you said?
Killed by lava.
Oh, killed by lava, yeah. Interestingly enough, now there's always that sort of disclaimer here. Interesting enough, you gain acceleration during the first few kilometers beneath the Earth's surface because the density of the surface material is much less than a condensed center. The mass of the Earth above you exerts a small backward pull compared to the disproportionately greater pull of the denser core material. So, because of different densities, there's some fluctuation for that. Blah, 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 blah. Blah, blah, blah. Shall we get a clicker? Go get a clicker.
Oh.
I apologize. I won't do it. If you stepped into a hole to the center of the Earth and made no attempt to grab the edges at either end, what kind of motion would you experience? Would you fall all the way through at a constant speed and stop when you reach the other side?
No.
Would you fall all the way through, speeding up the entire time and stop when you reach the other side?
No.
Would you oscillate back and forth with a changing speed called simple harmonic motion?
Always.
Would you oscillate back and forth with a constant speed?
Yeah.
Simple kinematics motion.
See.
Which one do you think? A is out, B is out. You think it's C? I think it's C too. Let's see what happens here. You would oscillate back and forth with what is called simple harmonic motion, just like a spring bouncing. Each round trip would take nearly 90 minutes. Interesting enough, we'll see in the next chapter, and you won't, that an Earth satellite in close orbit about the Earth also takes the same 90 minutes. The International Space Station and all of your cell phone satellites takes 90 minutes to go all the way around. Same motion as up and down, interestingly enough. I wonder what's here. I'll click there and I'll go on to the next page. Halfway to the center of the Earth, would you weigh more or less than you weigh at the surface? Halfway to the center. Would it be more, less, or the same? Half radius, half weight. You would weigh less. You would weigh less because part of the Earth that pulls you down is counteracted by the mass above you that pulls you up. Okay? Blah, 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 blah. Oh, why do I have two of those? I must have cut, yeah. Didn't mean to do that. You would weigh about half. Okay, let's talk about weight and weightlessness again. Review. Force of gravity, like any force, causes acceleration. Objects under the influence of gravity accelerate toward each other. We're almost always in contact with the Earth. For this reason, we think of gravity primarily as something that presses us against the Earth, rather than as something that accelerates us. This pressing against the Earth is a sensation we interpret as weight. Stand on a bathroom scale that's supported on a stationary floor. The gravitational force between you and the Earth pulls you against the supporting floor and scale. By Newton's third law, the floor and scale in turn push upward on you. Located in between you and the supporting floor are springs inside the bathroom scale. The springs are compressed by this pair of forces. The weight reading on the scale is linked to the amount of compression of the springs. If you repeat this weighing procedure in a moving elevator, you would find your weight reading would vary, not during steady or constant motion, but only during accelerated motion. If the elevator accelerates upward, the bathroom scale and floor push harder against your feet, and the springs inside the scale are compressed even more. The scale shows an increase in your weight. This picture, if you can't understand this, you need to look at this picture real close. Normal weight, constant speed, right? Here, the elevator's doing what?
Going up.
Accelerating upward, greater weight. How can you tell it's accelerating upward? Got the little cartoon things here, right?
Because there's an arrow.
Here, accelerating downward. Again, the cartoon cloud thingies there. Less weight. What if it snaps?
No way.
No way. What about that old myth that, if you're in an elevator and the cable snaps, when you almost reach the bottom, you should
Jump.
jump. Is that going to work?
No.
Of course not. Came up with that stupid idea.
What?
What's going to happen to you? You're still falling. You're still accelerating. All that's going to happen is you're going to extend your life by about 1/1,000,000th of a second.
You're gonna still splatter on the floor of the elevator.
I think that's something for some people were safe at the cable. Like, it snapped on top of you.
So what should you do if the elevator? You better hope.
That's when it would be appropriate to get out your cell phone and text everyone you know.
It's like,
You better hope.
Hey, I got about 15 seconds before I die. Nice knowing you. Take a selfie.
You better hope there's
About to die selfie.
there's a lot of people in
We're
there.
gonna start.
Okay. I think you're done listening to me. Oh no, hang on, I gotta talk more. So like, if you define weight as gravitational force acting on an object, then you still have weight whether or not you're freely falling. I'll be done in about 5 minutes, I promise. I see you falling asleep out there. Astronauts in Earth orbit who float freely inside the capsules are still being pulled by gravity. Okay, don't get the idea that there's no gravity there. Not true, and therefore have weight. But you in the falling elevator and the astronauts in the falling satellites don't feel the usual effects of weight. You feel weightless. That is, your insides are no longer supported by your legs and pelvic region. Your organs respond as though gravity were absent. You are in a state of apparent weightlessness. When astronauts go up to the space station for months at a time, their body actually decreases. They lose muscle mass because they're not using their muscles to stay upright anymore. They have to.
Like, Earth says what, 9.8, isn't the moon's like 2 something?
1.6 on the moon. To be truly weightless, you would have to be far out in space, away from the Earth and other attractive stars and planets where gravitational forces are negligible. Even way out there in Pluto's orbit, still being attracted to the sun. In this truly weightless condition, you would drift in a straight line path rather than the curved path north. In more practical sense, we define the weight of an object as the force it exerts against a supporting floor or weighing scales. According to this definition, you are as heavy as you feel. The condition of weightlessness, then, is not the absence of gravity, but it is the absence of a support force. It's not the absence of gravity, it's the absence of something holding you up. That queasy feeling you get where in a car that seems to leave the road momentarily when it goes over a hump or worse off a cliff is not the absence of gravity. Again, it's the absence of a support force. Astronauts in orbit are without a support force and are in a sustained state of weightlessness. This causes space sickness until they get used to it. I wonder what this could possibly be. Let's see.